Hey everyone, welcome to my playlist on single variable calculus. So in the last lecture we talked about concavity of a function, concave up and concave down, and its connection with double derivatives. Okay, so today we are going to talk about the concept of inflection points, IP, inflection points. So we will see the definition of inflection point. We will try to understand the definition of inflection point. Many times people are very much casual with the definition, that's why I am keeping a separate lecture on inflection points. Then we will see what is the condition to find the inflection points, and we will see some nice examples and the counter examples. So this session will make sure that your concept on inflection point is clear. Okay, so if you recall my earlier lecture, I gave you a homework problem. I don't know how many of you have solved, but I asked you that if I take sin x from 0 to 2 pi, you have to tell me in which interval, you were supposed to tell me in which interval the graph is concave up or the function is concave up, and in which interval it is concave down. So you have to do that by double derivative, but by looking at the graph also you can see. So from 0 to pi, as you can see, you take any 2 points, the line is below the graph, therefore from 0 to pi it is concave down, and from pi to 2 pi you take any 2 points, you draw the line joining the points on the graph, then the line is above the graph, so here it is concave up. So at pi, at this point, at pi comma 0, at this point the graph is changing its nature, so it is going from concave down to concave up. So the points where graph changes its nature, then such points are called as inflection points. So here this point is called as an inflection point. Okay, so the point where concavity changes, then such points are called as inflection points. But there is one more condition to this definition, which I will state it and then we will spend some time on it. So here is the definition: a point where graph of a function has a tangent line. I have underlined this because people usually tend to forget this point. Okay, so where it has a tangent line and where the concavity changes. If these 2 points are there, then such points are called as points of inflection. Okay, that's one thing. Now see, existence of tangent line, I'm not saying that the derivative should exist at that point. Okay, it should have a tangent line. Now once you have a tangent line, you can have two cases. For a tangent line, either the derivative will exist or it does not exist, right? So for example, if you have a vertical tangent line, then does the derivative exist for vertical tangent line? No, the slope is infinity, minus infinity, whatever. So the slope derivative does not exist, but yeah, tangent line is there. Okay, and if the line is not a tangent line, then the derivative will exist. Okay, so don't get confused. Okay, tangent line is given, that means the derivative exists. No, once you have a tangent line, if it is a vertical tangent line, then the derivative does not exist. If you have a non-vertical tangent line, then the derivative exists. Okay, so let me give you this example on this so that it will be more clear to you. So if I take the function as, say, x raised to 1 by 3, if I take f of x equal to x raised to 1 by 3, if you don't know the graph, those who don't know, they can use GeoGebra or any software they wish. At 0 you have this, like, it goes very close to this 0 kind of vertical line you have. This is a graph of x raised to 1 by 3. Now at 0 you can see the vertical line is the tangent line. Okay, so and you can see here also, what is f dash of x? It is 1 by 3 x raised to minus 2 by 3, and therefore f dash of 0 does not exist because it is 0 means 1 upon, what is this? This is 1 upon 3 x raised to 2 by 3. So you have a 0 in the denominator, therefore f dash does not exist. F dash at 0 does not exist. What about f double dash of x? It is minus 2 by 9 x raised to minus 5 by 3. So which is minus 2 by 9 into 1 upon x raised to 5 by 3. So here also f double dash of 0 does not exist. So vertical line is the tangent line, but the slope or the derivative does not exist. Okay, so it has a tangent line. Okay, now that was an example where I wanted to say that the tangent line does not imply that the derivative exists, because you may have the vertical tangent line. But now here you can observe one more nice thing. See, when your x is positive, then this quantity is positive, but this is negative. So f double dash is negative. So for x greater than 0, your f double dash is negative. That means, what does that say about the function? Your function is concave down, and you can see over here it is concave down. You take any 2 points, the line is below the graph. So for x positive, your function is concave down, and when your x is negative, then I am taking its fifth power, which is negative, taking its cube root is negative. So this is negative, this is negative, so product is positive. So for x negative, my double derivative is positive. So therefore for negative part, the function is what? Concave up. And you can see from the graph, you take any 2 lines, the line is above the graph. So therefore it is concave up. Okay, so if the derivative does not exist, don't say that there can't be an inflection point. Your f dash and f double dash at 0 does not exist, but still you have an inflection point. Okay, so for inflection point, we need that the tangent line should be there, which is there in this case, vertical tangent line, and the concavity should change. So here also concavity is changing, therefore origin is the point of inflection. This is your IP. Fine. Okay, now how to find inflection point? So let's try to see that. So now once you have a function, what to do? You find the derivative f dash. Okay, so you find f dash. What about f dash? You can say either it will exist or it will not exist. Okay, if f dash is not existing, now what to do is you find f double dash. Okay, so let me write down here only. You find f double dash. So since f dash is not existing at a point, obviously your f double dash will also not exist. Now for this you find f double dash. Now f dash exists. So now f dash will either exist or it will does not exist. So for a function, either f double dash will exist or it will not exist. Okay, so if it does not exist, okay, it's fine, you keep it aside. If it exists, suppose at C, f dash exists, then what can you say about f double dash of C? Now suppose C is the point where your concavity is changing. Then the question is, what can you say about f double dash of C? It has to be 0, right? Because if I'm saying that at C the concavity is changing, that means what? So for example, this here it is concave down and then it is concave up. That means here for this x, if I take x on the left side of C, then what can you say about f double dash? Your f double dash has to be negative because it is concave down, and here over this x it is concave up. That means f double dash is positive. So when I'm going from negative to positive, definitely I'm going to cut 0. So at f double dash of C here, it has to be 0. Or other way, if it is concave up to concave down, then also same thing, f double dash is positive, f double dash is negative. So at here the concavity is changing. Therefore at f double dash at C f double dash has to be 0. So at C, if you are having an inflection point and if the double derivative is existing, that means what? The double derivative has to be 0. Okay, and therefore one can say that, therefore one can make a note or a statement that if C comma f of C is an inflection point, then either double derivative of C does not exist, or if it exists, then what can you say? It has to be 0. Okay, so inflection point implies one of them should be there. So whenever there is a question on you have to find the inflection point, you find the double derivative and then see at which point double derivative does not exist and at which point double derivative is 0, and then check whether those points are really an inflection point. Okay, see, this is the necessary condition, this is not the sufficient condition. The converse is not true. If you're not comfortable with necessary and sufficient condition, what I want to say is the converse is not true. If this is happening, that does not guarantee the inflection point. So if I give you f of x, the counter example to the converse. If I give you x raised to 4, what is f dash of x? It is 4x cube. What is f double dash of x? It is 12x square. And when f double dash is 0, it exists because it's a polynomial. And when f double dash of x is 0, when 12x square is 0, that means your x is 0. But so my c is 0 over here. So what is f of 0? 0. So is 0 comma 0 means 0 comma f of 0. F of 0 is 0. Is this an inflection point? No, because if you recall the graph for x raised to 4, x square is like this. So x raised to 4 will be something like this. This is the graph for x raised to 4. If you don't trust me, you can use GeoGebra. Okay, so, and you can see that you take any 2 points, the line joining the points on the graph is above the graph. Therefore, this is a concave upward graph. So here also it is concave up. Here also it is concave up. So at 0, the concavity is not changing. Therefore, this is not a point of inflection. Okay. So mere existence of the point where the double derivative of 0 are not defined does not guarantee the inflection point. So converse is not true. Okay. But if it is an inflection point, then one of them has to hold. Okay. So therefore, what you do is you find the double derivative, you equate it to 0. And see at which point it is 0 and at which point it does not exist. And then with those points you see whether concavity is changing or not. Okay, so therefore the converse is not true. Keep this in mind. It's like the same thing for what you have seen for critical points. Like if local maxima or local minima, then the derivative has to be 0. But if the derivative is 0, does that imply local maxima or local minima? No. So you can relate in that sense if you wish. Okay, that's one thing. Let me take one more example where it may happen that the first derivative exists but the second derivative does not exist, and that point is again an inflection point. So let's see that example. So take this as a function x raised to 5 by 3. Just see the graph for your comfort level. Find the first derivative. So 5 by 3 into x raised to 2 by 3. So yeah, it's differentiable everywhere because you first take a square, then take a cube root, it exists. Good. So f dash is differentiable. What about f double dash? This is coming out to be f double dash, and you can see that f double dash of 0 is not defined. So here the first derivative exists but the second derivative does not exist. So and is it 0 anywhere? No. When is the fraction 0? When the numerator is 0. What is the numerator? 10. 10 is never 0. So f double dash of 0 does not exist, and there is no point where f double dash is 0. Okay, now you have to check whether x at 0, do you have an inflection point? Okay, so what is f of 0? F of 0 is 0. So you need to check whether this is an inflection point or not. So see, what is x less than 0? What is the sign of f double dash? When x is negative, its cube root is negative. So whole thing is negative. So when x negative, f double dash is negative. For x positive, f double dash is positive, because cube root is positive, this is positive, so product is positive. So yes, as you can see at 0, f double dash is changing the sign. So therefore indeed at 0 f double dash is not existing, but it's a inflection point. So the ultimate upshot is whenever a function is given to you, you find double derivative and see at which point double derivative is 0 or does not exist. Once you have that, you draw a table. I will show you in the last example. The one which I'm going to take is the last example, and we will see that you just see that if the sign is changing, it's inflection point. If the sign is not changing, it's not an inflection point. So suppose your function is x raised to 4 minus 2x square. You find the first derivative, you find the second derivative, then you take the second derivative equal to 0, and when you do the calculation, your x comes out to be plus minus 1 by root 3. This may not be the inflection point. You need to see whether the double derivative is changing the sign. If double derivative is changing the sign, that means it's an inflection point. If it's not changing the sign, it's not an inflection point. Okay, so again the same thing. We drew a table when we were dealing with increasing, decreasing. Here also we will draw the table. Same table, kind of. You first write down the interval. Now here the domain is minus infinity to infinity. So you split the interval at those points where the double derivative was 0. For increasing, decreasing, you split the interval where single derivative is 0. For concave up, concave down, you split the interval where double derivative is 0. Then what will be the second row? Sine of f double dash. And at the end you can say whether f is concave up or concave down. Okay, so this is the table you are supposed to draw. Okay, now here if I take say minus 2 is in the interval. What is f double dash of minus 2? It is positive. If I take 0, it is in the interval. What is f double dash of 0? Negative. And here it is positive. So here you have concave up, concave down, concave up. So in this interval the function is concave up. In this interval is concave down. In this interval it is concave up. Okay, and here is it at minus 1 by root 3, is it changing a sign? Yes, from positive to negative. So yes, concavity is changing. So you find minus 1 by root 3 and find f of minus 1 by root 3. Then this is your inflection point. At 1 by root 3, is f double dash changing the sign? Yes. So therefore your 1 by root 3 and f of 1 by root 3, this point on the graph is also an inflection point. So I hope the concept of inflection point is clear. You may see this lecture again because it may happen that some examples may not be clear at first go, but if you see again, then example might get clear to you. Okay, now let me give you one last homework problem. So here is the question. You have to find derivative, double derivative, and you have to tell me what are the inflection points. Don't tell me the points where double derivative is 0. You find the points where double derivative is 0 and see whether at those points whether sign of f double dash is changing or not. If it is changing, then yes, those points will be the, c comma f of c will be the inflection points. So okay, tell me two things. Tell me the points where double derivative is 0 or does not exist, and tell me the inflection points. So that's what your homework is, and that's what you have to comment in the comment section. So yeah, I hope everything about the inflection point is clear. If you even have a small doubt, you can ask me in the comment section. And if you don't have any doubt, then do not forget to like, share and subscribe. Thank you.